Hello guys, welcome back to my channel. Before watching this video, please ensure that you go back and watch part 1 of this video. And please remember to like and subscribe. Now, before we go into the rules of the indefinite integral, there is something that we did in part 1 of the video that we need to go back and explore. So let us see if you recall. When we integrated 2x with respect to x, we all agreed that we would have gotten x squared plus c. So this is what we got as the derivation. We had used this to show you that integration as a reverse of differentiation, we can use differentiation to kind of give us or to guide us. Now, from a graphical perspective, what does x squared plus c mean? We know that the original graph y equal x squared looks like this. All right, so it's symmetrical about the y-axis. But x squared plus c, which means it's indefinite, we don't know what c is, which means that there could be millions, infinitely many curves of this form. What do I mean by that? So, and as a typical multiple choice question, you could have gotten this too. So probably, let me just put on some numbers here. 1, 2, 3. So let us say that we found that c was equal to 3. Then the curve would actually look like this. But what if c was 2? What if c was 1? Right? All the curves would actually be the same size. It's just because it's freehand why it looks like this. If c was 0, then the curve would actually cut at the point 0, 0. If c was negative 1, then would actually have that curve there. So what is actually happening here is that we have an entire family of curve being represented by x squared plus c. And if we were to get certain condition, of course, we could definitely find that curve. But we're not so interested in that now. We're looking at the indefinite integral. Let's go back to the rules. We know that when we were differentiating, so for instance, if you had the differential of a function or of two functions connected by plus or minus g of x, then we know that we could actually separate these functions by saying the differential of x, f of x with respect to x, plus or minus the differential with respect to x of g of x. All right. A similar concept is applied in integration. So if I'm going to integrate a function that is connected by plus or minus, so if we have f of x plus or minus g of x, then of course what we can do is to split the integrals. So it's the integral of f of x with respect to x plus or minus the integral of g of x with respect to x. And please to add this to your catalog of rules. Let us look at a simple example. So if I were to, for instance, have the integral of 3x squared plus 4x dx. In a case like this, what I could do is to split the integral. So I could say the integral of 3x squared dx plus the integral of 4x dx. We know the procedure. We say we add 1 to the power and we divide by the new power when it comes down to the polynomial. So I'm going to have 3x. If I add 1 to square, I'm going to have cube over 3 plus 4x squared, because the power there is 1, over 2 plus c. Now the question is, why don't I have two separate constants? It doesn't really matter. A constant is a constant, so having a plus c covers for both functions. So when I break this down, I would end up with x cubed plus 2x squared plus c as your constant of integration. And of course, in a case like this, we don't have to split a function as simple as this, but it's important to understand the conceptual idea behind it. Let us look at our next example. Now we know that when we were differentiating, the variable had to be in the numerator. The same concept applies to integration. Before I can start integrating, I must ensure that the variable is in the numerator. So I'm going to have to start by rewriting this function as 5x plus 6x plus, by laws of indices, I bring up the x cubed. I'm going to have 4x to the minus 3 dx. Now we can go right ahead. So because it's really a basic function, we don't have to split up everything. We can just go right ahead and integrate it as it is. So we take the 5x, when I integrate that, I'm going to add 1 to the power. So I'm going to have 5x squared over 2 plus 6x. Add 1 to that power, so I'm going to have 6x squared over 2 plus, if I add 1 to that power, negative 3, I'm going to have negative 2. So I'm going to have 4x to the minus 2 over minus 2 plus your constant of integration. And notice, because I had 5x plus 6x, really and truly I could have written it as 11x, right? So when I break this down here, I'm going to have 5 over 2 x squared plus 3x squared minus 4x to the minus 2 plus c. And we really don't want to leave it like that. So these are really like terms. So I'm going to have 11 over 2 x squared. Now that x to the minus 2, I can refine it by taking back down x to make the power positive. So we can say 4 over x squared plus c. Looking at this example, we would not have given you a rule for integrating a product, which means that we don't know what to do in this case, so we're going to have to get rid of the product. So we can expand this bracket. So I'm going to have the integral, put my big bracket here, 4x times 2x, I'm going to have 8x squared plus 16x plus 12x plus 24. And don't forget the dx here. Now, before we start integrating, always look for like terms. So in this case, I'm going to have 8x squared plus, I'm going to have 16 plus 12x, that's 28x plus 24 dx with respect to x. Now, once you have done that, we can go right ahead and integrate. So when I integrate 8x squared, I'm going to have 8x cubed over 3 plus 28x squared over 2 plus, when I integrate 24, I'm going to get 24x plus a constant of integration. Of course, you do understand why we get 24x there. We can think of 24 as 24x to the 0. So if I add 1 to the 0 power and divide by 1, I'm going to end up with 24x. Now, we always tidy up our integrals. So we can say 8 over 3 x cubed plus 14x squared plus 24x plus c. Here's the next example. So in a case like this, we're going to have to manipulate it so it becomes a simpler form to integrate. So what we can do is to simply split this. So what I would have is the integral. We could go 6x squared over 2x plus 4x cubed over 2x dx. Alright, now simplifying this, I'm going to end up with the integral. So by laws of indices, x into x squared is like 2 into 6 is 3. So I'm going to have 3x plus 2 into 4, that's 2. And x into x cubed is going to give me x squared dx. And we simply just integrate this. So I'm going to end up with 3x squared over 2 plus 2x cubed over 3 plus c, which we can simply rewrite as, and if, of course, if you notice here, 3 over 2, well, we could simply rewrite this as 3 over 2 x squared plus 2/3 x cubed plus c. And if you want, you could put it in descending order to say 2/3 x cubed plus 3 over 2 x squared plus c. If we look at question A, we notice that we have radicals. This is not a problem because we know by laws of indices that we can manipulate these functions. So first I could go right ahead and write this as the integral, where I have the root x, I could say 6 over x raised to a half power plus the cube root of x. We could write that as x raised to 1/3. Of course, the rules remain the same because the variable that I'm differentiating must be in the numerator. So I'm going to have to bring up the x to a half. So when I bring that up, I'm going to have 6x to the negative a half plus x raised to the 1/3 power. And bear in mind, you have the option of splitting the integral and working them individually, or you can work it collectively. Now, when I add 1 to that power, I'm going to add -1, negative a half to positive 1, which is going to give me a half. So I'm going to have 6x to the half over a half plus I'm going to add 1 to 1/3. So I'm going to have x raised to, power here will be 4 over 3, and I divide by 4 over 3, plus my constant of integration. Now when I divide 6 by a half, I'm going to get 12 x to a half. And of course, when we divide by 3 over 4, we really multiply by 3 over 4, x to the 4 over 3 plus c. I have the option of putting back the radical if I want. So I could write this as 12 root x plus 3 over 4. Now, of course, the denominator gives me the cube root of x to the 4 plus c. I don't have to, but I could. So whenever we have radicals, we just have to change them out to rational numbers. We're now going to look at worked examples with trig functions. Now, from my previous video, we would have established that the integral of sine x with respect to x is negative cos x plus c. Also, that the integral of cos x with respect to x is sine x plus c. So those are what we're going off. Now, let us say that we're going to add to these two. Now, let us say that a is a real number. All right? And I would want to integrate. So I'm creating a general rule here. Sine of ax with respect to x. If we were differentiating, we would have differentiated the ax, which would have given us a. We differentiate the sine, which would have been cos, and we multiply the a by the cos of ax. But to reverse that rule now, we carry out a similar concept. We differentiate the ax, which is a. But instead of multiplying this time, the reverse of that is to divide by a. So what I'm going to end up with is 1 over a. Now, we established that when we integrate sine, we get negative cos. So I'm going to put the minus at the front, and I'm going to have cos ax plus c. Similarly, if we were to integrate cos ax with respect to x, we differentiate the ax, which is going to give us a. So we're going to have 1 over a sine of ax plus c. Now, here's something that persons normally get incorrect. Now notice that, or recall rather, that when you differentiate cos x, you get a negative sine x. But when you integrate cos x, you get the opposite, which is a positive sine x. When you differentiate sine x, you get cos x. But now when you integrate sine x, you get a negative cos x. So it's important to establish that connection so you don't get mixed up, because persons normally get questions incorrect because of that mistake. All right, let's put in a simple question. So what if I now had the integral of sine 6x minus 4 cos 2x with respect to x? All right, so we can look at the sine 6x first. So we differentiate that 6x, which is going to give me 6. So I'm going to have 1 over 6. When I integrate sine, I get negative cos. So we put a minus at the front, and we have cos 6x. Looking at 4 cos 2x, the 4 at the front, as we know, will not affect the integral rather, of the cos 2x. So we differentiate the 2x, which is going to give me 2, and I'm going to divide by that. Now, since we already have a 4 at the front, we can say 4 over 2. When I integrate cos, I'm going to get sine, so I'm going to have sine 2x, and I add my constant of integration, which is c. So this breaks down to give me negative 1 6 cos 6x minus 2 sine 2x plus c, your constant of integration. All right, let us look at an example where we involve a polynomial and a trig function. And once again, we say because it's connected by a plus sign, we can choose to split the integral. It's not a complex integral, so we can actually keep it together and we can manipulate it. So this becomes the integral of 4x to the minus 2 plus 8 sine 4x, and all this with respect to x. And of course, you remember how we integrate the polynomial. We add 1 to the power and we divide by the new power. So I'm going to have 4x. If I add 1 to negative 2, I'm going to have negative 1 over negative 1. Alright, for the 8 sine 4x, you can ignore the 8 at the front for the time being. Looking at the 4x, when I differentiate that, I'm going to get 4. So we know we're going to divide by that 4. So I'm going to have plus 8 over 4. Of course, when I integrate sine, I get a negative cos. So we're going to have the minus at the front there. And we're going to have cos 4x plus the constant of integration. Now, of course, we don't want to leave it like this, so we tidy it up. So we have negative 4x to the minus 1 minus 2 cos 4x plus c, which if I manipulate, I'm going to end up with negative 4 over x minus 2 cos 4x plus your constant of integration. There we go.